Okay, let's get started. So today will be our third and last session on ROP. And we will look at one more example and talk about how do we defeat ROP. So we'll take a look at the challenge first. Then we're moving to defense. After that, we come back and so you can work on this challenge. So this is the ROP2 challenge. The reason I designed this challenge is to let you to practice a very specific gadget. So let's take a look. So we have a main function. The main function calls volatile. Volatile has a buffer, 200 bytes. Then we open, we get an exploit from a file. From the file, we read 190 bytes, but the buffer we ask for is 200 bytes. So there is no buffer overflow here. However, the next several lines will make sure that you can override two things in this function. The first one is the return address. So first, I get the return address at a C code level. So the whole piece here is trying to get the return address. So we have a local variable I, and we know that the local variable I is, so this one will 32-bit. So the local variable I is, the parameter I is 4 bytes, and it is at an address 4 bytes higher than the return address, right? So at C code level, I can get I's address, then I can get the return address on stack by -4. So that's the purpose of that. Then your input, the first 4 bytes will move to the return address on stack, where overwrites the return address on stack. Okay? So even though there is no buffer overflow here, then there is no sequential buffer overflow with F8, but you can overwrite the return address. So that's the first thing. The second thing is your second 4 bytes in your exploit will be moved to the register EAX. So the syntax here is AT&T syntax, not Intel syntax. So the 0 here represents the first argument here. Then we move that value to the register EAX. So you got to overwrite two things here, in total 8 bytes. We are only working on 32-bit of this. If we work on 64-bit, I need to change this part a little bit. So you are overwriting the return address. You are overwriting EAX. That's it. So if you do there is no print flag function in the address space. And the stack is not executable. You cannot inject the share code there. So the only way you do this is, well, with our current knowledge, the way you do this is to do a ROP. So in ROP, you need to control the return address, right? The first, you control one return address, then the return address points to, you override that, points to the next gadget, always the next gadget, you chain them together. So here, besides controlling the return address, you also control EAX. However, you do need the stack. You do need to override a lot of addresses or even put some data on the stack, right? So the gadget I want you to use is the stack. We call it the stack pivot gadget. We talked a little bit about this. So basically, you find an exchange gadget, exchange instruction to exchange the value of EAX to ESP, the stack pointer and the value of EAX. There are similar gadgets like that, like a pop, ESP, return. So the goal of this, but for this specific one, you have to use a change EAX one. Okay. So the first return address, you're gonna overwrite must point to a gadget like that. And that gadget will swap the value in year X with ESP. And in year X, you compute that. So the purpose of this is you create another stack. And let the ESP points to your own stack. And that is a stack you can control. And that one you can use environmental variable or whatever, because there is no code there, it's just data, right? Data and address. So this is a challenge we will work on later. So at 32-bit level, we can find those gadgets. We use the same tool, ROP gadget, we use to find those. And this can be a environmental variable to build your own ROP changer. Okay, so we will work on this later. Let's finish other parts first. So now you have some good understanding of how ROP works. Like I said at the very beginning, many people have been developing new techniques beyond ROP, such as jump-oriented programming and call-oriented programming. So the difference is the last instruction in their gadgets are not a return instruction, but a call instruction or a jump instruction. The call can be an indirect call, can be a direct call. The jump can also be a direct or indirect one. Indirect one means something like call EAX, call RAX, or register. Direct one is a hard-coded address in the instruction. So this is a paper that proposed the jump-oriented programming, which was published 13, 14 years ago in Asia CCS. Asia CCS is a conference that is always hosted in Asian countries. But Asia here actually stands for application security, whatever. Okay. So they proposed this paper, the idea of jump-oriented programming. That's why if you use our ROP gadget tool, you can also find those job gadgets, not just the ROP gadgets. However, it's not easy to pull this off. If you have time, go read the paper. You will understand that you need some specific gadgets to pull this off. And it's not easy to find those gadgets in at least for Linux systems. I think if I recall correctly, in their paper, they find gadgets on Windows libraries. So I tried to find those gadgets on Linux, but it was not successful. So it's not easy to do this. Another very interesting, really interesting paper published 10 years ago in IEEE Security and Privacy was called Blind ROP, or the paper title was Hacking Blind. So this idea is a great idea. So far, we are doing all kinds of reverse engineering before we hack, right? So in buffer overflow, we reverse engineer the code. We say how big the buffer is. Then we know how to construct our exploit with some padding there, then fittings, then with the address and everything else. In ROP, we do the same thing. We know where the buffer is, how big the buffer is, and also we know the binary that we are hacking. We use a tool called gadget to find gadgets in the binary. Okay, the binary could be the library, could be the program itself, but we know the binary. We do not necessarily have access to the source code, but we have the binary and we can find the gadgets and we know their address, right? So in this paper, they propose a more generic way to do ROP without knowing the binary. You do not have access to the binary. You cannot reverse engineer where are the gadgets. You do not even know what gadgets are there. You just keep trying, and eventually you find all the gadgets you want. Okay, so let me explain a little bit how it works. First, we'll assume there's ASLR, and we have a session talking about ASLR, and we have some way to defeat that, right? In ASLR, only the in our current Linux system on x86, only some middle bytes in the middle will be randomized. Maybe 16 bytes, no, 16 bits, something like that, will be randomized. So in our, we have several challenges. One of them is we only overwrite the lower bytes instead of the middle bytes. So the middle bytes, we do not even overwrite it, right? So even though they are randomized, we do not overwrite them. They stay intact and they are still correct. Another approach is to use the same approach we have tried to guess the calorie value. Remember, how did we guess the calorie value? We overwrite each byte. If it crashes, then we know that's not correct. But this approach only works for programs that use a fork to create a child, right? Because the child will have the same calorie value. But a lot of programs on the internet, the servers, the HTTP servers, web servers, they are programmed that way. There is a fork. There is a parent process, create a child process to handle all kinds of socket communications. And the child process will have the same calorie value and also the same address space, ASLR. We're talking about this because ASLR right now is only performed when the program is created. So the child process will not re-randomize, right? Existing systems work that way. So we can use the same approach to break ASLR for those kind of web applications, web server applications. After we overwrite, we'll find the calorie value by overwriting one by one. We keep overwriting. We keep overwrite the return address, okay? Until we find one return address that will not crash the program. If it doesn't crash the program, then we know the middle bytes, several bytes in the middle, they are the correct ones. Otherwise, usually they'll crash the program, right? So how do we know if they crash the program? So remotely, we just observe whether the socket is still open or the socket is pending. If the socket is open, it means the program is not crashed. If the socket is closed by the remote party, means the web server is, at least the child process is crashed and they reset that socket, right? So by this way, by using the same approach, technically we can break ASLR. And in this paper, this is called the stack reading approach. You just probe writing different values so that one by one, byte by byte, eventually you can understand the, you can get a return address on the stack. After you get a one return address on stack, it's easy for you to guess the other addresses in the address space. That return address on stack could be a library address. Maybe it's a callback function from a library to your program function, or the program you are, the piece of function you are hacking right now is a library function. You don't know. So it could be a library function. It may be a libc function there. Then you will find out the libc address for everything, right? Even though you do not have access to the libc library running on that machine, you have other versions of libc. Maybe they have the same version and not many differences there. You can find the relative address for other functions. Right? Then you need to find the gadgets here. You can overwrite that return address to any place. Any place. If you write it to a place there is no valid gadget, or let's say if you return to an address with a valid gadget, like pop RBI return, eventually what happens? There is a valid gadget, a good gadget, and you blindly put a return address there, and the child process on the victim machine eventually execute the other gadget. Then what will happen? We'll be able to observe that. Not really, right? Because let's say that's something like pop RDI, then return. You cannot debug that. You do not observe RDI, but eventually it return. So if we're looking for the next gadget, so very likely it will crash the child process again, right? So even if you find a valid gadget there is no way for you to tell if it's a valid gadget, and there's no way to tell what gadget that is, right? So in this paper, they introduce a new approach, which is a very smart approach. They do not look for the gadgets we have been looking for so far. So the gadgets we are looking for so far, they have some very specific functionality. Pop a value into RDI, pop a value into RAX, or do something else. They look for another type of gadget they call the stop gadget. Okay, so stop gadget basically is a gadget that will not trigger the program crash right away. So our pop RDI return gadget will trigger the segmentation fault right away. Yeah, but if there is a gadget that will not do that, it could be there is a sleep function then return. The sleep function will take like 10 as parameter, sleep 10 seconds, and this can be observed remotely. In this case, remotely on the attacker's machine, the socket, you will not see the remote socket is closed. Instead, it's still alive for several seconds, something like that. So the first step is to find a stop gadget like that. You only need one of those gadgets. Okay, you keep trying, you find one of those gadgets. After you find those gadgets, you just need very specific gadgets to you are finding you are doing a write operation to write the memory of that victim process to your socket file descriptor. Okay, so what are we doing that? We're dumping the memory of the victim program. Okay, so if we successfully dump the victim's address space, the memory content remotely to our local machine, then we can find more gadgets, right? So the first step is to find a write operation. And the write, you already know, write is basically put, so the write, the first argument is the file descriptor, then the buffer, the address you want to write, then the size, maybe the other parameters, right? Then you need to find gadgets to pop to RDI, pop to RSI, and maybe a size. Size should be RDX, but probably that's not important anymore because very likely RDX value will not be 0. Then in the paper, we call those gadgets the blind growth gadgets. Okay. To find those gadgets, yeah.
How do you conclude that you found one of those?
So the trick here is you already know a stop gadget.
Yes.
So whatever gadgets you are trying, after that gadget, you put a stop there.
Yeah.
So then when you try something and that crash, then it will not stop. It will crash right away.
Yes. Yes. I get that part.
Okay.
I guess what I'm having a hard time wrapping my head around is how I know, yes, I put something in,
yes,
I popped something in RDI.
That's a good question. I do not remember exactly how they did that. There are several tricks.
I could see maybe that stop for RDI, whatever's in RDI number of seconds then.
No, I think it's not about that side channel. For example, to set the RDX, they're not really looking for RDX, top RDX return gadget. They are looking for a string compare function, and that function will somehow set RDX. Okay. So for this gadget, they were looking for RDI and RSI, and I don't remember how they confirmed that. Yeah, that's a good question. Yeah, but eventually they will use ASR to find after breaking ASR, they will find the right function code, not the system code. Same as what we did in class. We didn't do a right system code. We do a function code. Right? So eventually after that, they get the binary. So they dump the binary. After they dump the binary, then they can find other gadgets. Then they can build build a share code like what we build, basically. So yeah, go ahead.
So when you write the binary from the root socket,
Yeah.
Like does the DOM memory will contain both the parent and processes?
Child and parent process will have the same thing in their code section. Yeah. So this is a hacking blind idea. In their paper, they tried this approach blindly on some web servers, and they were able to. Obviously, everything is automated. They were able to hack this with thousands of requests because you're basically probing each byte and you're making thousands of requests. It takes like some of them take 10 minutes, some of them take longer, 30 minutes, but we'll eventually be able to dump the memory and we can create more sophisticated shortcut. Okay, so in general, how do we defeat those kind of approaches? First, let's look at what conditions do we need to pull off this attack? The first condition is we need to subvert the control flow to our first gadget, which usually means we need to control the stack, we need to control one return address, and we have the stack calorie to defeat that. But now we know that we can easily defeat stack calorie, especially if the process will create a child process, they will have the same stack calorie. We can also use ASR to do that, but we just learned ASR can also be easily broken using the same approach with break calorie. Then we also need to control the content on the stack. We do not necessarily need to inject code there. We don't inject code there, but we do need to control the stack. We need to put many addresses on the stack. We also need to put some data on the stack, right? We should find enough gadgets in the address space. And so far, that's not difficult. We use the rob gadget tool. We find all kinds of gadgets there. And we need to know the address of those gadgets with ASR, which means we need to break ASR to find the address of those gadgets. Then we should have the ability to start execution anywhere to find more gadgets. Okay. If we cannot do that in RISC architectures, if all the instructions are 4 bytes or 8 bytes, everything is aligned, we can only jump to 4 bytes or 8 bytes, we can still find gadgets, but those will only be gadgets emitted by the compiler, right? But here, as we see in last class, the gadgets we are using, they are not emitted by the compiler. They're just maybe data part of one instruction or just the lower parts of one instruction. So the first idea to defeat this, this is a very generic approach. It's called the control flow integrity. We actually already studied part of control flow integrity, which is the shadow stack part. Okay, we talk about shadow stack. There are 2 stacks. One is the original one. There's a different one. And we use several instructions easily to put another copy of all return addresses in another stack, right? And that stack is called a channel stack. So when we return from a function, we may compare the returns. There is a call instruction to G. So from F to G, that is a legit control flow graph. But if any other place from F to G or F to other places, it's not a valid control flow graph. And this problem can be simplified if the code section is not writable. Most of the cases, our code section is not writable, which means the direct calls, like for a fixed address, like this. This is a direct call. Then we have an indirect call, which is like call RAX, right? So if our code section is not writable, this part can never be changed, right? This will always be legit because attackers cannot change this. However, this can be subverted because the attacker may somehow change the value in RAX. So when you execute this instruction, RX has a value that it is not supposed to have. Make sense? Yeah. So channel stack only care about this, right? So this is basically a return. So for channel stack, whenever there is a return, you will push the return address to another stack. There's another copy of the return address. Yeah.
So that is how keeping that target. Right?
Yes, but it only protects the backward end. It doesn't protect this one. Right. Yes. So this one, so we're mainly talking about the indirect calls, not the direct ones, because direct ones are easy to protect. We just need to make sure the code section is not writable. But the indirect ones are difficult because the RX will have a value at runtime, and you need to make sure that value is a legit value.
The indirect calls are reproducible forwarded to that.
Yes, exactly. Yes.
Why didn't indirect calls, because the code section you are getting only the offset or something?
No, there are many reasons. There are a lot of function pointers in the program. Not necessarily the developers explicitly use function pointers, but many languages they implicitly use that as well. For example, the V tables, in C++ object, the virtual tables. Every object at the beginning that's a virtual table, they are all function pointers. So the compiler, because of the what is that, polymorphism or whatever C++ provide and other object-oriented language provide, you do not really know, the piece of code doesn't know which exact function you are calling until you know which object it is, the type of object. And because of that, that must be an indirect call. So let's say we already talked about this. So this is one example. We have a full function here. The first local variable of this function is a function pointer. This is a function pointer. And there is an input for the user. If the user is magic, we are going to set the function pointer to a bar function. That bar function. Otherwise, we set a bad function. Okay. Then we are making a function call here. Okay. So in this case, if we do a program analysis, we will know that there are at least two legit destinations for this function call here, right? It can be either this one or this one, at least two. But those kind of program analysis is not easy. First of all, the program analysis is not easy. Second, there may be errors in those kind of analysis. Second, if we want to enforce that, what we can do is before this function call, this is an indirect function call. This is not at the binary level, but eventually you can imagine this will be something like a core RAX or RBX, and you put those functions address in that, right? So before we make this function call, we can check. We do a runtime check to check the target here, whether it is either this one or this one. Everything else is not allowed, right? So in one of the challenges you have done so far, there is a pointer, there is a function pointer. I remember it's a buffer overflow challenge. There is a function pointer on stack, and you override that. And also the behemoth challenge is like that. There is a function pointer. As long as you override that, you can you can call anywhere you want, right? So if we have a check like that, then we can check if the destination is one of this. Then we can make sure it will only jump to one of this. Even if it calls one of this, there may still errors, right? Because let's say you are user magic, you're supposed to call this function, but user magic somehow overwrite this function pointer to Bass, and you call Bass. If we make a check here that to check if it's one of this, it's still not really a valid one, right? But at least you cannot call to Bass or Boost, whatever, right? The problem is this check can be quite expensive computationally, and also getting the set of valid destinations is also not that easy at compiler time. Not that easy. That's why existing approaches, the LLVM already have CFI built in the compiler. I believe GCC also has some, maybe, yeah, but LLVM already have that. They are using some more coarse grained approach. They are looking at, for example, they are looking here. We only check it actually calls to a function address. As long as it's a function address, it's okay. It doesn't really care the function type, which function. So we know that at least you're not calling into a random gadget somewhere. Okay, you are calling into an existing function emitted by the compiler. Yes, something like that. Start a function, yeah. Not just middle of a random instruction. Yeah, something like that. So that's why CFI is still a very hot area for research, because there are so many problems we cannot solve right now. But this is the basic idea of CFI. So in my lab, we also do some research on CFI. We try to make it more secure, or we also try to make it faster. That's basically our research. Yeah. Go ahead.
Would you go over the code of that works?
What?
Would you explain the code that's injected by that work?
So this is the channel stack.
Oh,
Yeah. The backward is basically the return. The return part, you can do the same way as the forward part. For each return, before each return, you instrument what are the valid locations for this return. And those valid locations are computed at compiling time. You can do that. So then it will provide the same level of security as the forward edge, which is not very good. Because you can say here, the problem is you do not know the context, right? Like the example I give you. Let's say we allow either bar or Bass. Then even if the user magic can override this to Bass, and there's no way you can identify that, right? Technically, it's still invalid, but you cannot identify because you don't have the context. Yeah. But with shadow stack, you get a more fine-grained approach that you know you know you are only returning to whoever called you before, right? So here, when you return, you are only returning to whoever called you. And you do not need to know a list of valid return destination.
Why if the user equal to magic, then it will be only function will be equal to bar, right? Not that.
That's just the program, that's the business logic of this piece of code. It could be anything.
But it will not be bad, so it will be bar. How can it be bad?
What if the
If you
the user magic overrides that function? That's what I'm talking about. The user magic is attacking this. So when you are user magic, you are only supposed to call bar. But this is under attack and change. The attacker cannot change to any place, any arbitrary address in the grid. Body can't change fast. That is still technically still invalid. But this approach will not be able to identify. There is another paper talking about context sensitive CFI, talking about those issues. Yeah, very complicated stuff.
like always be a better like or like with a function that you're not calling something about combined files. Right?
Yes.
That's what it-
Yes. Yeah, so this will be, so how this is implemented, so forward or backward, they are implemented at compiler level. You already say that for shadow stack, we didn't change the, do we see examples of shadow stack? Yeah, we show some assembly. We didn't really, so we didn't really say how compiler did that. Right? So usually it's compiler implementation. So you do not need to change the source code. The compiler will automatically add some code there, and that process is called instrumentation. Okay. Instrumentation means add or change something there.
You said under context to your file.
Yeah.
Where exactly do you need the context? We have the context, the bar and the paragraph.
Yes.
The valid function. That is the context, right?
Yes. So here, basically, the context means when the user is magic, the legit destination should only be bar. It cannot be bans. Yeah.
Right now, it is only the function is bar or bar,
Yes.
but the context is good.
Yes. Yes. That's so different level of security will consider different things, right? So most existing compiler process or CFI, they're probably only checking if the address, if this one is a function address, the first instruction of a function. They're not even checking the type of the function. Then you can imagine a second level, a little bit better than this is to not only a function address, but also the function prototype should match the prototype here, right?
We are making a control program.
Yeah.
This program.
Yeah.
Won't be by default, to do like, I don't understand, by no to be user magic.
It's very difficult. It's not that easy.
So we have, when you, right now, this check, forward check is not involved in the control program.
Depends on what kind of information your control flow graph want to include there. It can be, but even this is not very easy. Imagine control flow graph is static analysis. And you need to find all those information accurately in static analysis. It's not that easy. There are a lot of errors. Yeah. So that's CFI. Let's say this is one example. There is a jump. So in this case, it's not even a call, it's a jump. But it's an indirect jump ECX. This is the exact example in the original paper published in CCX. So they were instruments, several instructions before the jump. And those instructions were compare the target. So in the original approach, what they did is they put a label in the destination. We put a label, let's say, we have a jump ECX, and this is a valid location to jump to. This is a legit location. But obviously, this location is in the middle of the function, right? It's not really the beginning of function because it's a jump. Then they put an ID here. It could be a random number. Then other legit locations may have the same ID or may not have the same ID. Okay. Then when we jump, before we jump, we will retrieve the ID from the destination and compare with a hard-coded value here. And that is a legit ID we must jump to. Then we compare if the target destination address have the same ID. Okay. So this is called the ID-based CFI. And the granularity can be controlled by how do you assign the IDs. Imagine this is a random number, okay? It kind of like a very random number. When you compile this program, those target addresses, they are going to instrument or insert a random number in front of the target address. Then, before the jump instruction, there will be checks to check if the target address have those random numbers. It must be the correct random numbers. If they're not correct, then we just kill the program. Go ahead.
Does the IDs keep memory at compile time?
Yes, compile time. Yes.
So every ID has to be unique, otherwise.
That's more like the policy part, right? So a lot of security solutions, we have the policy part, we have the mechanism part. The mechanism is like this. The policy part defines what kind of clarity we want to have. If we only want to, let's say if this is a call, and we only want to, the security we want to provide is the call has to call a function. We don't care what function. Then at the beginning of each function, we can put an ID there, and all of them have the same ID, right? If we want to say the call has to call into a function that has the correct prototype, then all the functions with the same prototype will generate the same ID for it, right? So that's more like a policy, but the mechanism is the same mechanism. Make sense? So you can say in this case, our target is ECX. Then we put an ID there, 1, 2, 3, 4, 5, 6. We compare that with the ID. If it's wrong, same as channel stack, we just print out something, we exit program. Otherwise, we eventually jump there. So this is the ID-based implementation of this. So this is proposed in the original paper 20 years ago. Okay, then to pull off Rob, we need to know the address of the gadget. Go ahead.
I think we have already implemented.
LLVM already have this implementation. I'm not sure about GCC. I think GCC may have something. Yeah. LLVM have some options, and they provide different levels of CFR. Yeah. But we haven't seen so many real-world deployments yet. The performance is one of the problems, and also the predefined CFG, that's also another issue. So we have a paper published 2 years ago. We're doing CFI on embedded systems, and we always assume the predefined CFG, the control flow graph, can be easily retrieved. It's actually, yes, because it's not that easy. It means in reality, you may get a CFG which has many errors. Yes, it's not that accurate. But we're talking about indirect ones. So if it's like either like this is direct one. This is easy. This is direct one.
This ID is
No, not with IDs, with like core EAX, core RAX. Those indirect ones. It's not that easy. Yeah.
and they're And the indirect also.
To make it, so this is a trade-off, right? So correctness and let's see, security. You can make it always correct by covering more addresses. Then it's more fine-grained. You will allow all kinds of attacks as well. We talked about another paper 2 weeks ago, the control flow bundling attack, remember? Control flow bundling paper. Yeah, when we talk about the format string, the last slide I gave you is is for control flow bundling. Okay, the control flow bundling proved that with current CFI differences, because it's fine-grained, it allows you to go to some addresses. Now, you do not need to go to arbitrary address. You can go to limited numbers of addresses. But just by going to those limited number of addresses, you can do a Turing complete computing, even with just format Turing complete computing.
Then there's fine grain.
Yes, it's not fine grained.
Fine grain is better.
Fine grained is better, but it's hard to get a fine grained policy or
It's actually fine grain is better. How can I both be good like that?
it's not fine grained enough.
Oh, okay.
Imagine what is the most accurate one.
Fine grain, but I
Yes.
can study.
It's relative, right? So when I say fine grained, coarse grained, it's relative. Yeah. Go back here. There are many ways to look at this. The most strict policy should be if it's user magic, you can only call var. When you are other users, you can only call bands. You cannot call anything else. Okay. But this is very difficult to achieve. Yeah.
So that 9 years statement in your like assembly, right? But you know that is something that then be
Yes, that is related. That's a hardware feature. Yeah. Now we're still talking about software-based features.
Right. Is the ID stored in your code section?
Yes. Yeah. In this example, you just insert ID in front of it's like before the prologue of the function. You put a random number there. Yeah. So to defeat Rob, you can also make randomize the address, randomize the gadgets, so it's harder to find it. But we know that this is not working either. There are many ways to get information leakage, so you can know the address of different things, including gadgets. Okay, so that's why the third approach is to remove gadgets. By removing gadgets, it means we remove the return instructions. Yeah. When we talk about rob, then we're talking about the remove return instruction. What is the return instruction? What? No, return instruction. Return instruction is basically C3, CB, right? That's 1 byte. C3, CB, C2, CA. So what if in our program, we never use those bytes? We never use those bytes. Yeah.
How would you like put the intelligence?
Hmm?
How would you put that to one? Yes,
Okay. So return is basically doing what? Return is doing a popping, right?
Oh, yeah.
Return is pop ESP to EIP, right? 64-bit, I think there are some tricks you can play without really using return. And also, you can simply reduce the number of return instructions. You do not need to eradicate every return instruction there. So a lot of gadgets we say so far, they are not really emitted return instructions by the compiler. They are just a C2, C3, CB somewhere in the instruction and can be interpreted as a return instruction. If we remove those, reduce the number of those, we can significantly reduce the number of gadgets as well. So the idea of this paper is to, we just do not have those. Let's say there is a jump instruction. The jump instruction here is a relative jump. It's going to jump to an address which is say 8 bytes away from current location, right? This is a jump. But because of this jump, there is a say 8, and this say 8 will be treated as can be treated as a return instruction, and it will give us some valid gadgets. Then we just remove this, right? Then we jump to say 9 instead of say 8. Now after that, we create a loop instruction, right? So we jump 1 byte further, but the next byte, there is nothing, right? So this is exactly the same as what you do in the share coding module. You try to write share code and you try to avoid some bytes, right? So here, the same idea. We try to avoid some bytes. Yeah. More examples. There is a add C2 to year X. C2, the value of C2 is same as return. So what we do is we can add C1 to year X and we increase year X. Same as what you did in share code. So you see, doing research is not that hard. Yes, so if you have a list of what conditions we need to pull off this attack, take out one condition, you can publish paper. Yeah.
Like the ASCII code.
Exactly. Yeah. The ASCII share code. You guys only do ASCII share code, right? We can do any other one. I have other challenges for share code as well. Yeah. I think the most interesting one I probably want you guys to do as a bonus point is to we still ASCII share code, but you are not allowed to use the int 80. Okay. Because right now I not allow you guys to use int 80, right? The idea is very simple. You have a first piece of share code, okay? That piece of share code will change the second piece of share code and to make a int 80 there. Yeah. So before you call that, before you call int 80, it was something else, some other instruction. Then you change it. When you execute that, it becomes int 80. It's not that difficult. So we can do that as well with bonus points. Another example, there is a CA. Yeah, we just change that. Right? So this is another way to defeat ROP. Just more example there we can skip. Yeah.
I wanted to know like how does the CPU know when the inspection ends? Because in Intel there is no fixed inspection.
You don't know. What do you mean?
So CPU will execute inspection one
So-
after the other.
So CPU will fetch instruction from the memory, then decode that, right? So from any particular address, specific address, the decoding is deterministic. It can only be interpreted as one instruction. Yeah, at any address.
That's why you can jump between the
But if you jump to the middle, it becomes it's just one instruction, either a valid one or it's not a valid one. Yeah. But it cannot be interpreted as two different instructions. That's for sure.
encoding will handle that.
Yes, that's a hardware thing. Yeah. So this approach, we try to remove gadgets from the address space. Another approach is instead of removing gadgets, instead of detecting or before the attack, we stop the attack. We just monitor the execution of the program. We have a trace of the program execution. The trace may have all the instructions the program has been executed. Then if we are doing a ROP, like what we did before, what we will say in a trace. Any other idea? What were we saying?
Yeah, different brands.
Okay. So basically, we will see a lot of return instructions, right? So if it's a normal function, you will have all kinds of other instructions. Then you have a return, right? No one will always program a super small function that has only one statement, then return, right? But if it's a ROB, at least the ROB we have been doing so far, it will be just 2, 3 instructions, even 1 instructions, then there's a return. There'll be so many returns. So use that as a heuristic, just the percentage of return instructions in the trees we can detect. We can use that as the indicator to guess if there is a ROB attack. So that's another idea. This one published in Usenix also 10 years ago. It's just to monitor that. And also modern CPUs, they offer something like a tracer. We actually use a tracer for one of our projects for CFI. Is that tracer will tell us the last 200 or 300 instructions the CPU has been executed. Okay. And some tracers can even tell for a specific process what are the instructions it has been executed. So this is more like after miss. After attack has happened, we look back to say if there has been attack. Okay, then we have what you were asking, the hardware-based approach. Now, this, yeah.
So it would be, if you see whatever happening, you can
Yes.
try to see and attack up or down.
Yes. So in this way, you don't even need to do a tank analysis. Just check how many return instructions are there. Set a threshold. If there are 30% of the instructions are returns, that's not normal. Yeah, as simple as that.
But if the attack already happened, then it would be like a detective.
Yes. So then the key here is how often you check the trees. You can check the trees after every 50 instructions have been executed. So maybe the attacker was able to do some kind of ROB, but not necessarily get what they want to get. They haven't dumped the secret yet. They haven't get the flag fire yet, but they have been executing some instructions. The perfect solution is CFI, but assuming you need to have a perfect CFG, which we don't have. But even CFI, the problem is performance. That's why we still have a job and we keep working on this. Okay. The next approach, this is a new hardware approach. Intel has this feature called a CET. I don't remember what that stands for. Intel Control Flow Enforcement. Yeah, something like that. Yeah. The idea is actually very similar to the forward edge CFI. Instead of putting a label there or ID there at the beginning of function, they put an instruction at the beginning of the function. This instruction is in this case like NBR32. ARM has a similar feature. They have an instruction called BTI, branch target something. Okay. So the idea is if there is a call instruction or jump instruction, the call instruction and jump instruction has to jump to a NBR32 instruction, NBR64 instruction. It cannot jump to an AND instruction or call to an AND instruction. So the call will always go to the beginning of the function, right? So this is actually a coarse grained CFI. It's not very fine grained. This is coarse grained CFI that the jump will only go to the beginning of this, and hardware support to make it even faster. So you don't need to instrument. You don't need to instrument the check. Previously, we instrument the check before the call instruction that take several instructions. Now we do not instrument that. Whenever we execute this instruction, the CPU, the hardware level, circuit level will check. Is the instruction before the instruction or call? Right? And on call, we'll also check, if after the call, if the next instruction is and the UNDBR instruction. It's a very small state machine, basically. There's 2 states. And obviously, those instructions, they are in the space of for older instruction set, they are in the reserved instruction space, which means they are basically NOPs, no operations for older CPUs. We're not going to do anything. Okay, so that's it for all the differences I know so far. There's still a lot of research in this area. Attack and defense. And you can say the one that have been deployed are not perfectly secure. Performance is very important factors when those manufacturers, no matter which level, hardware level or compiler level, when they consider what to implement, performance is here the most important thing they consider. Okay, we still have some time, I believe. How much time we have? We still have like 30 minutes. Then if you haven't finished, how many of you got the first rock chain one? You got that? Okay. So if you haven't got that one, then you can work that one. Okay. After that, you can work on rock 2. Yeah.
32.
32-bit. Yeah, this one we're doing 32-bit. So Thursday, we will talk about heap attacks, which is another very important topic and very practical. The buffer overflow one, it's the foundation, but it's not very practical anymore. The heap attack is very, very popular in recent years. So we will spend 2 sessions or more on heap. Then we can talk about maybe we only have 3 classes left. So I'm thinking if I should cover a little bit about cache side channel attack, because that's also related to memory corruption now. It's used to be, it's not really directly related to memory, right? It's the inside CPU, it's what we call micro architectural level. But now those techniques has been combined with memory corruption attacks to do something sophisticated. So I think we will cover a little bit of that. But there are a little bit more of memory corruption we need to cover, including the secure memory safe languages like Rust. And we will talk about that a little bit as well. And there is a keynote speech I want you guys to watch. The keynote was given by a professor from Georgia Tech several years ago at CTS. And that keynote was talking about we need to switch to Rust. Okay. I don't know why Rust is our new hope here, basically, several years ago. And the last year, the Biden administration, they released, I don't know what they call it. It's more like a White House, more like a recommendation from the White House or whatever, talking about we need to switch everything from C++ to memory safe languages. Not necessarily Rust, but right now, for low-level programs, Rust is the only option. Rust, I don't know how successful Rust will be, or maybe the memory safe language after Rust will be super successful, or Rust itself could be super successful. Also, I'm thinking about a research project of translating embedded C code or C++ code automatically to Rust with the help of large language models or whatever. So if you guys are interested, we can talk about that too. We have been doing a lot of embedded system hacking those years. Also, I will send you guys an invitation, invite you to do a CTF with me next semester, the semester-long CTF. it's like I told you guys before, we develop a secure system for 2-3 months. Then we hack other teams' system. Yes. In the last 2-3 years, several teams has been using Rust, but not necessarily in a very safe way. They use a lot of unsafe blocks, which basically still have all kinds of memory corruption problems. We wrote a paper about that, and it's under review at the Usenix. Yeah. So if some of you will join my team to do the eCTF, then we will look at that paper too. Okay, cool. We have 30 minutes to work on this too. Yeah. I will be working around to help you with this. the homework of this week is four mark string challenges. I think I demoed at least three of them in the class. One of them we didn't demo that. But you already learned all the techniques to do that. Yeah, this is the one we didn't do in class. 4 mark string 7. And there's no source code for this one. You only have binary code. Okay. But this one, you said this is. Pretty late, so you want to do it on them. Oh, yeah, yeah, that is fine. Yeah, we'll do the good. Okay. Before we get them, so we don't get the candidate, because we are overwriting the candidate in this one. When the candidate comes at the last, yeah, candidate, yes, yes. Exactly. Yeah, you get a, there's dereference, getting a segmentation for first. The question is, why don't we get the hex values first and expand in this case like this? And even in this case, so even if they're overriding the candidate. But the printer should be printing those first. That's because the kernel will buffer that. It will buffer and the packet they will kind of okay. Yes. Yes, it's the kernel will have its own buffer, and that's why there's a C library function called flash or flash. If you really wanted to get it all, you can call say flash. In this case, yes, we get lower than 34, so everything was buffered. Yeah. If we did not get a full, then we bring it out. Yeah, I think so. Yeah. Yeah. And this one is the slide for the last picture. We're just putting that streaming data and when it is not roughly. Well, two, it's slightly different because it's 32 bits, right? So you need to, and in my slide, I think I only have, yeah, this is 64. So, but idea is different. The idea is, yeah, there's this. No. So it's for 32, you can, so we have to solve 64 or 32. 32. Only 32. No 64 for this one. Yeah, because I was calculating the offset at one before and not matching like this. Yeah. Well, the address were never matched, right? Because every time we into the system, there was a different. But even with bootstrap, every time will be different. And a different version of it, say everything. So the only thing that we are putting our string in the data, this is data of the binary. You don't necessarily need to use this and saying, but it should be but this is data which you know what is binary, binary. But deletion will also work.
But if we're using some global way we do.
You may override
It will.
bots. You're just doing like 20 instructions, right? So it's less likely you're overriding some super important global variable that will crash the program.
And if they're using, if you overrode some variable which has been used by open or central, then it's not optimized.
Yes. But 32 also is because it's
You need to pass the line.
yes, exactly. That's actually makes sense either. Yes,
You need to find the gap.
exactly. You don't need to bind again. Yeah,
And it's.
yeah.
Lot.
It's more like a return to be safe.
Normal. Reason.
But the first gadget will be I want you to use that exchange gadget. That's what.
Well,
In the row too. Yeah. This gadget, you have to find a gadget like this. Of course, yeah.
oh, I was talking about.
Oh, you want to talk about this one? Oh, this one you're doing 32 bit.
Yeah, this one you have to do 32 or 64 or both.
This one 64. Only 64. 32 will be easy. 32 will be
32 is just normal.
return to be safe.
This one you just control the first 8 bytes and the return address and the RAF.
Yes, yes, yeah,
From there we do something.
yeah. Yeah.
Getting the bulk of one, so
Ah, yeah, show me your command.
so I did this.
Okay, so the offset is one. The offset should be off. So it will be offset,
Hmm,
yes. You are LDD first.
I thought I did that, but
You are LDD. This is not the same library. Yeah.
I see. So that I investigate here. Okay, okay, that makes sense. Okay, not understanding. How this code works. Okay. That makes more sense. I'm looking forward. And yeah, so I would. I'm assuming. I put what I want to do in the environment variable. I put. A paper to the environment variable in EAF. And the command is paint that in EXP. And maybe the 12. And down to 12.
Yeah. You're basically your share code is a raw chain, like in the environment.
Yes.
Just address.
Yes.
And there's another trick from here. And you don't know the exact address, you're gonna say maybe that you're watching in the environment variable, when you leave some kind of knob there.
Okay, so I find some knob inside of the command return.
But that knob is not a really long instruction. Address. You do that. Follow along that. Instructions.
I thought that was a. Gadget that doesn't do anything.
Yeah.
Yes.
What kind of guarantee is that?
One that just depends.
Yes.
Yeah.
Basically, all the time.
Yes. Yeah.
Return the address of your one return instruction there, and link to it, the address of the rules from there.
Yes. Okay, cool. That all makes sense. Thank you.
Oh, no, yeah. Yeah. I think the value from the module was very, very good. Our education. So. Hold on. Roll two, roll one, roll one. Roll one. Yeah. It's like, well, overflow is, overflow is important. Yeah, but maybe it's a thing. Yeah, because I developed the back. Yeah. Yeah. Yeah, you definitely. It's someone, it's always, you never done it, yeah. No, I never had a chance to talk to them. Yeah. Not.
Very impressive, very good. And I'm getting myself confused. I'm assuming I'm trying to recreate this with one of the realms. I cannot remember for the life of me what a friend of this is.
So here. You're not exactly doing it.
Okay.
The reason is, this is probably flat. Yeah, this is
Okay,
flat.
okay, then that turns the EDX into a pointer towards flag.
Yeah.
Okay,
You still need to make the function work. Yes, instead of.
Mhm.
So this is a system call.
yes,
But the problem here is with the system call, you don't have a gadget.
Yeah. Mm.
It's hard to find a gadget like that. So you need still to make a function call. Or you make a 32-bit function call. The previous one, I'm making the 40 function.
okay. And then another question was, this packing method.
Yeah.
Is the significance, what is the significance of this key? Is this,
Q means 8 bytes.
okay,
The power. We need to change that to double word.
Okay.
Mhm.
okay, cool.
Yes.
Yeah, you doing the
First one.
yeah. That overflow regulation for I guess. There's many there about this one. No, okay. So basically, I think I am all party one. Here, this week, all RTF, all RTF.
Yes, so yeah, those are three questions, right?
Yeah.
Then here, oh, yeah, that's like.
Oh, yeah. Dude, there's a implementation for.
The drawing is bug.
Yeah.
This one can make it similar.
Right.
Yeah, so if we use the value.
I will create.
ISI, simple, pop ISI.
Oh, yeah.
That's too long.
Right.
But pop ISI returns, if I am getting that. Pop ISI.
And I gotta have three. That should be cool.
You just put a lot of three features, like for other pop, you say there's a pop, you put a value one.
Oh, yeah, I got it.
That's- Yeah. That wouldn't matter, like, I mean, we done, there, right? Yeah, we need all there. It's only the people.
And I think I always.
Why are you actually there?
Yeah.
You know, the moving are zeros.
The zeros are there.
This is.
Uh,
Oh,
is there?
oh, yeah, that's it.
Yeah. And so I think.
Yeah. Maybe during the Anton Hamlin, I think, Not fully controlled, you need to be doctors that you switch on the longest.
Oh,
These are
okay.
Actually,
Then,
actually, you go to the beginning of your haircut, then follow.
One by one.
One by one.
Oh,
It works and you. Do that thing, taking.
first line. Oh.
No, this is a. You can run that script, and the output of the script is the input to a program. So that is a Python script, right?
Yeah,
So if you run that Python script, it gets some output. And that output is the input of the program, not the script itself,
oh,
right? Not the script
all
itself.
right, kind of runs.
Yeah.
Okay, I got it, thank you.
Yeah. Okay, folks, see you Thursday.